We're going to develop an expression for another simple geometrical object. In this case, it's going to be for the horizontal plate, a horizontal magnetic plate. And think of that plate as consisting of a sheet of negative poles on the top, overlying a sheet of negative poles on the base, and those sheets of poles are separated by a distance L. And in the x direction, minus infinity to infinity. And initially here we're going to do the y direction from minus infinity to infinity. But right now we're going to take a look at a line of negative poles. These poles have the same pole strength P, the intensity of magnetization M over V. M is the dipole moment, magnetic dipole moment, the product of the pole strength times the pole separation. And I is basically equivalent to the pole strength divided by the area, dy dx, which is basically a pole strength per unit area. So, since the magnetic field intensity of an isolated pole is P over r squared, the field of this small area here is P over A the area, and then dy dx, which is the area. So we get P over r squared. But we're integrating over dy and dx in order to get the effect on the magnetic field intensity of this entire strip going from minus infinity to infinity. So that becomes an integration. And our integral looks like this. Just looking at the negative poles, we're integrating from minus infinity to infinity, P over A dx dy over r squared. R would just be, if we're, should have put that in here, but it's down here. We've got an observation point, some point above the strip, and we're looking at the influence of this particular piece of the strip. And we're also interested in the vertical component. So we take h sub s, in order to get that vertical component, we have to multiply this by the cosine of theta. So this is the integral that we're working with, and just kind of putting it together and going through the steps. This is kind of our starting point here. Now, we can make a substitution for dx, where dx is equal to r d theta over the cosine of theta. Remember, we did this when we were working, we were trying to determine what the Bouguer plate correction was, and we did this for the gravitational field over a plate. Of course, in gravity we just have monopoles. In magnetics we have dipoles, so we're doing the set of negative poles here, substituting for dx. So we get rid of 1r. We also get rid of a cosine of theta here, and I'm not showing all the steps, so try to follow along there. And then we can also see that r is equal to m over cosine of theta, so we have one remaining r here. That turns into m over cosine of theta. So that cosine of theta that we canceled out, we reintroduce, so that over here, and now we're integrating over theta. So instead of going from minus infinity to infinity, we're going from minus pi over 2 to pi over 2, cosine of theta d theta. And we have the intensity of magnetization over m, which is the distance from the point of observation along a line drawn normal down to this strip. So this is the basic integral that we have to evaluate. And when we go through that integration, cosine of theta d theta, we get the magnetic field intensity of the strip is equal to 2 times I over m dy. So we have one integration left here, dy. So now we're going to take a look at, we're going to let m equal r now, and this could have been the strip that we were looking at, and we were calling this m, but we're going to call it r now because r is a variable, and it's going to go out along this entire sheet. So we have h for an individual strip that we just came up with was 2 times the pole strength over the area times dy over m is now going to be 2 times the pole strength over the area times dy over r. So now we're going to be integrating out along the y direction. Each one of these strips, the contributions from each one of these infinite strips. So just like we did, we can substitute for dy. dy is going to be r d theta over the cosine of theta. And make that substitution. For dy, we get this integral here. Again, we're integrating from minus pi over 2 to pi over 2. 2 times the pole strength over the area times r d theta. The r's are going to cancel out. The thetas are going to cancel out. We just end up with 2 times the pole strength over the area integrating over d theta from minus pi over 2 to pi over 2 instead of minus infinity to infinity. And that's a simple integral which gives us, when we substitute I equal p over a back into this expression, we get 2 pi. We have the factor 2 times the integral from minus pi over 2 to pi over 2, which would be pi over 2 minus a minus pi over 2, which would be pi. This is 2 pi times the intensity of magnetization. Now we have to do this for the positive plate and the negative plate. But before we do that, let's just mention that in the y direction we don't necessarily have to go out to plus and minus infinity. This could be a plate that's fairly extensive in the x direction, but may not be infinite in extent in the y direction. So we could just be doing the y integration from a minus theta over 2 to a plus theta over 2, where this total angle here would be equal to theta, and then that integral would be equal to, considering just a negative plate, that would be equal to 2I theta or 2 theta I. So now we have to visualize two sheets, and so think of these as sheets instead of just strips, but a sheet of negative poles at the top, sitting on top of a sheet of positive poles on the bottom. We're going to sum them together. So we have these two sheets going out to infinity in the x direction, plus and minus infinity, but not going out to infinity in the y direction, going out to theta 1 for the negative poles and theta 2 for the deeper set of positive poles. So we have the contribution to the magnetic field intensity of the plate from the set of negative poles. In other words, again, think of this as a sheet going from minus theta 1 over 2 to theta 1 over 2 times I d theta. That gives us 2 theta 1 I. And then do the same for the set of positive poles. We're integrating from minus theta over 2 to theta over 2. That gives us minus 2 theta 2 times I. And then we're going to sum the two together so that we get the magnetic field intensity of the plate, consisting of both the negative poles and the positive poles, be equal to 2I times theta 1 minus 2I times theta 2. So if we think of this, theta 1 and theta 2 are fairly small, then we could think of this as a rod. And so what I'd like for you to do is to consider this problem. We've already worked at two different ways. We worked at one assuming that we could represent this wall by a horizontal cylinder. We also assumed that we could approximate it using a sphere. It doesn't seem reasonable. I mean, it just gives us a small anomaly. Remember, we got 5.4 nanoteslas for the sphere. We got about 18 nanoteslas for the horizontal cylinder. Now what I want you to do is to do it using this formula that we just derived. And now, theta 1, well, you could take the inverse tangent of 1/2 of this 0.5 over 1.5, inverse tangent of 0.33, and multiply that times 2, or you know how to figure out these angles, so we'll let you do that. Remember, these are going to be in radians. So if we want to figure out the magnetic field intensity of this wall, we can use this equation for, let's call it a rod, and we'll get 2I times theta 1 minus theta 2. Now what I'd like for you to do, again, this problem is we have this volcanic, this wall which has been composed of volcanic rock. So we're at an archaeological dig. We're trying to find out where everything is. We know that we've got magnetic materials that are buried at the site that are forming the walls that are made. Susceptibility contrast to 0.001 CGS units. Magnetic field intensity of 55,000 nanoteslas. So determine the wall's detectability. And we've already done that. So really in this case, what you're going to be most interested in is to see if the magnetic field intensity associated with this rod is similar to the magnetic field intensity that we obtained using a horizontal cylinder. So let me know what you find out, and we'll talk more about this next time. Thanks for joining us.